Okay, this video covers section 9.6, Intro to Functions. So in this section, we're going to look at what is a function. We're going to think about domain and range, and then we're going to look at function notation. Okay? And then when you get to Math 112, you do a lot with functions. Okay, so any set of ordered pairs you can think of is going to be a relation in two variables. There's nothing special about it. No special conditions have to be met. Any set of ordered pairs, any table, anything you plot in a coordinate plane, like in a two-dimensional coordinate plane would be a relation. But let me change to red. But a function, I meant to do all this in red, but a function is going to wind up being special. It's got a special condition. A function is going to be a relation in which for each x value there is exactly one y value. Okay. All right. Now, functions are real common in like your everyday world. For instance, if your taxable income turns out to be a certain amount, then there would be one. Well, that's kind of a bad example. Let's go to a gas station. If you and I go to the same gas station and we both put 10 gallons of regular gas in our gas tanks, we're both going to be paying the same amount. All right. So for a particular X value, like 10 gallons, there can be only one Y value matched up with, one cost that you'd have to pay for that. When you have that situation, you have something that's considered a function. So if you and another person have the same job and you're supposed to be getting the same pay rate, then if you work 10 hours and they work 10 hours, you would expect to earn the same amount. Wouldn't be fair otherwise. So I kind of think of functions as being fair. Okay. All right. Now, with a graph, so you can represent a relation in two variables in a variety of ways. If you have a graph, you can see if each x has only one y by using something called the vertical line test. The vertical line test. So if there is a place where a vertical line, that's this kind, goes up and down, crosses the graph in more than one spot, it is not a function. So let me show you. So like if you had this relation of two variables, a vertical line would only cross it in one spot. It is a function. So that would be a function. That is a function. Okay, if you had something that looked like, say, this, vertical line would cross the graph in no more than one spot. So that is a function. But if you had that parabola turned over, a vertical line would hit the graph in two spots. That's what would make it not a function. So that's the vertical line test. If a vertical line hits the graph in more than one spot, then it's not a function. Okay. Now, sometimes you don't have a graph and you don't feel like trying to graph. You just have maybe the list of ordered pairs or a table. So if you have a table or a set of ordered pairs given to you somehow, just a list of ordered pairs, you can check if the relation is a function by making sure that no two different ordered pairs have the same x value. Okay. All right, so let's do an example. So if you had an ordered pair among the set that was like 3, 1, and then somewhere else you had the ordered pair 3, 7. If the x's are the same, picture what's going on. If you plotted those points, 3, 1 and 3, 7, they would line up above one another. They would be located above one another. if they were plotted, and so the relation would fail the vertical line test. So even though when I'm given a table or a set of ordered pairs, I still think about how they would look if I were to graph them, and I just think about the vertical line test to decide whether I've got a function or not. Now you do have to be careful. Some people think that the same y would be a problem, but like if you had the ordered pair 5, 2 and the ordered pair 5, negative 3, 5, 2 would be here, 5, no, I meant to put sorry, that's not the example I meant to do. If you had the ordered pair 5, 2 and the ordered pair 3, 2, the ordered pair 5, 2 would be here, and the ordered pair 3, 2 would be lined up to the left of it. That would still be a function. Okay? That would still be a function. It would pass the vertical line test. There's no vertical line that would hit those points in more than one spot. It's like a horizontal line is okay. It's the vertical line that's a problem. It's called the vertical line test. So this would be okay. This would not be a function if the x's were the same. But if the y's are the same, it'd still be a function. All right, with an equation, it can be kind of complicated to tell until you get more experience. You definitely can't have y being raised to the second, the fourth, or any even power like x equal y squared. Okay, because like if you did have the x equal y squared, the y squared would equal x. If you tried to solve for y, you'd have to square root both sides, and there'd be two square roots, both the positive and the negative. So for a particular x, like say 9, you would have two y's matched up with it. Like 9, 3 would work, and 9, negative 3. Okay, you'd have two y's matched up for a particular x. There's other issues. X equal y squared would be a sideways parabola, so it'd fail the vertical line test. X equals absolute value of y would be a V shape on its side, so it would fail the vertical line test. And most inequalities, when you graph those, they look kind of like this, and you have to do this shading, and this would wind up having all these points, so it would clearly fail the vertical line test. Okay. All right. So let's go ahead and look at a few problems that you might be expected to do. So here we have a set of ordered pairs. They could have been given to us in a table, right? So instead of looking like that, they could have said 1, 3, 2, 3, 3, 3, 4, 6, something like that. All right, notice that all the x's are different. Or think about if you were to plot these, 1, 3, 2, 3, 3, 3. They line up 1, 3, 2, 3. 3, 3, 4, 6. None of them are above one another. So this is a function. Number 1 is a function. Okay. On number 2, I'm looking at it, and I have a 2 for an x, a 3 for an x, a 4, and here I have another 2. See, notice this point and this point have the same x value. So 2, negative 3 and 2, 1 would line up above one another. That means that set of ordered pairs does not represent a function. Okay. Now, this representation is called a mapping. These are mappings. Okay, both of these are a mapping. And it's whatever's in the circle where the arrows are coming from. That's like your x's. This is like your y's. Okay, these are like your x's. These are like your y's. So if you take a particular x, like Da Vinci, see how Da Vinci has both the Last Supper and the Annunciation matched up with him? Okay. Right there, the fact you have two arrows coming out of one x value, that's not a function. You have an x with more than one y. But see here how Lakers only go to California, the Spurs only Texas, the Mavericks only Texas, the Clippers only California. There's only one arrow coming out of each of those x values. This is going to represent a function. It doesn't matter that both the Spurs and the Mavericks are associated with Texas. Okay. That doesn't matter. you can have more than one x going into the same y value. What you can't have, you have to be sure that each input, each x, only goes to one y. Right? Now let's look at determining if y is a function of x by looking at a graph. So really here, this is pretty quick. This would pass the vertical line test. So yes, function. Okay, here when I look at it, note a vertical line would cross the graph in only one spot, so it's a function. Here, clearly not. See how I can find a vertical line that crosses the graph in more than one spot? Not a function then. Here, a vertical line would only cross the graph in one spot, then that's a function. Okay. Number 8 is a trig function. We use these to model things like the tides, high and low tides, or temperatures that fluctuate up and down. So over time, you've got the tide going in and out, and it winds up looking something like that a lot of times. Okay. All right, now we're going to look at the concept of domain and range next. The domain of a relation is the set of all possible x values. And then by possible, it's kind of an agreement. Sometimes I don't really make this clear to you, but by possible, we mean any real number you can plug in for x that results in a real number for y. You'll see some instances in a minute where we have some issues. You've already experienced that in both chapter 7 and in chapter 8. Okay. Now the range is the set of corresponding y's. So the important thing to remember is that the domain is your x's, the range is your y's. Okay. So on number 9, the domain would be the set consisting of the number 4, 3, and 0, because those are the x's of those ordered pairs. And the range would be the set consisting of 2, -1, and 1, because those are the y's of those ordered pairs. Okay. On number 10, the domain would be, I'm not gonna write it, but the domain would be all of these guys. Okay, the inputs, and the range would be Texas and California, because that's the y coordinate. That's where things are, those are the outputs. Okay. All right, when you're doing it from the graph, this is probably going to be the hardest thing for you to think about, to visualize. All right, on number 11, the graph appears to just stop right there at -3 and 3. This blue represents all of those ordered pairs that are part of the relation in two variables. All right, this is your x-axis, remember. This is your y. When you're doing domain, you should be thinking, what are the x's of these points that have been graphed right here? So one way to think about this, I think about it by, in my mind, smashing the graph. I'm trying to see what the x's are of these ordered pairs. So for instance, that ordered pair would have the x of -2. This ordered pair would have an x of 1. Do you see if I smash the graph, projected every point down to the x-axis, this is what would be covered up on the x-axis? The domain would be everything from -3 to 3. Now, interval notation, I used it in math. We haven't used it in this class, but in Math 98, we use it when we're dealing with inequalities. It's that parenthesis bracket idea. So we'd want all the numbers from -3 to 3, and we'd want to, it appeared that we would include the -3 and 3. Wasn't real clear. They didn't make it a big bold dot, but I'm going to. Okay. So assuming those endpoints are included. All right, so that's domain. All right, let's do the domain on these others, and then I'll come back and do the range. So domain is x's. So when I'm looking at these ordered pairs here, I'm thinking about what are the x's of those ordered pairs. Now these arrows mean this keeps going and this keeps going, right? So as you smash these points, project them to the x-axis, can you see that everything would be covered up? Everything from negative infinity to positive infinity. And you always use parentheses on infinities because you can't really ever hit the infinity. Okay, so all the real numbers between negative and positive infinity, that's really just saying all real numbers. Okay. All right, now with this one, let's assume that that stopping point right there is part of the graph, and then it looks like this. So we're going to project everything to the x-axis. These all happen to project down, but sometimes you would have to smash them up to the x-axis. We just didn't have any examples like that. So what I can see there is that what would be covered up would be everything from -2 to positive infinity. I'm thinking x's. What are the x's of those ordered pairs? -2 included, and then a parenthesis on the infinity. That would be the domain. Okay, so with domain, you're focused on projecting the points to the x-axis. All right, I'm going to go back, and I'm going to do what happens if I'm talking range. Okay, so let me clean this up. Get rid of the red. Okay, and for this, let me switch to black. And for range, what we're going to be focused on is what the y-coordinates of all the ordered pairs you see are. So one thing nice about the graph is the ordered pairs are in front of you. So think about that as a set of ordered pairs. Think about this as a set of ordered pairs that goes on forever. Think about this as a set of ordered pairs, right? Set of ordered pairs right there. Okay? So if you're looking for the y's, the range is the y's, the domain was the x's. You're looking for what the y-coordinate of these points would be. So let's think about that. So if I'm sitting right here, the y-coordinate of that point would be 1. The y-coordinate of this point would be up there. This one would be there. This one would be there. So what you got to do is smash the graph, what the points on the left and right, just smash them towards the y-axis. And can you see that it would cover up this area of the y-axis? It would cover up from 0 to +3. And it appears that those would be included from 0 to +3. You got to switch gears. Your brain has to be thinking about y-coordinates, the y-axis. The y-coordinates would be how far up or down you are. So all these numbers from 0 to 3 would be the range. Okay, now on this one, when you picture these ordered pairs and you figure out what the y-coordinates are by smashing to the y-axis, don't forget to smash all of these. You wind up having everything from there up. Do you see how that point of the V is the lowest point? And it's at 2, and then it keeps going forever on up. That would be 2 to positive infinity. I'm going to do a bracket on the 2, and then it just keeps going on up. All right, I'm looking for the y values of these points. So this point would have a y value right there, these y values. This point would have a y value right here, and this keeps going. So I would have y values from 0, and it would just keep going on up, 0 to infinity. Now it can sometimes go to negative infinity and all of that. So sometimes people think of it as leftmost, rightmost for domain, leftmost, rightmost, leftmost, rightmost. And then for range, it's like lowest, highest, or bottom to top, bottom to top, bottom to top. Okay? All right, now, one more thing on domain. There's really not a lot of domain issues. Let me erase that bottom to top so you can see the words better. Okay, so there's only only a few functions where there are domain issues. You've already encountered them. One of them you encountered in chapter 7, one you encountered in chapter 8. We just weren't talking about them in terms of functions yet. Okay, so with rational functions, this was chapter 7. Remember those rational equations that you were asked to solve? And you remember how you always had to check to make sure it didn't make a denominator 0? Or you might remember the very first thing you had to do is try to find restricted values. And that was because you can't have a 0 in the denominator because division by 0 is undefined. All right, so remember how domain is the set of all possible x's? So any x that makes the denominator 0 must be ruled out, must be excluded. It's not possible. Okay. So when you see a function and you see that you have denominators, you would have restricted values, right? X plus 5 would equal 0 if x were equal to -5. So -5 is a restricted value, right? The domain in words would be all reals except -5. Now, sometimes what we do is we just say x can't be -5, but sometimes they make us write it in interval notation. So if you think about it, you can be any of these numbers, you can be any of these x's, you just can't be that. So in interval notation, it would be -infinity to -5, open parenthesis, you're not allowed to be -5, union that with -5 on. Okay, and you may or may not have had much experience already with interval notation. I don't think you have to deal with that much. Okay, so all real numbers except -5. X can't be -5, but can be anything else. And then interval notation is what I did with the parentheses. All right, so that's one type of function that has a domain issue. Another kind would be if you had radicals that have even roots, square roots, fourth roots, that kind of thing. Okay, with that type of function, you can't have a negative number under the radical, since that would cause the output to be imaginary, which is not a real number. And so it can't be graphed in the coordinate plane, right? Remember how what you're allowed to use for x are real numbers that when you plug them in, give you real numbers that come out. So when you have a square root or something like this, when you're looking at this right here, notice that if I put in a 0 for x, that's a real number. If I put a 0 in for x, I would have square root of 0 minus 4, which would give me a negative under the radical, and that's not a real number. And the agreement that we have, what we think of as the domain, are real numbers going in that produce real numbers coming out. This would be one of those imaginary numbers. It would be 2i, okay? So that means 0 is not part of the domain. All right, but it's not the only thing that would be a problem. Okay, so the idea is that we need this x minus 4, the part under that radical, to be bigger than or equal to 0. As long as it turns out to be a positive number or 0, we're okay. So I can find that by just adding 4 to both sides, and I can tell that the domain would be the set of all x's that are bigger than or equal to 4. Okay? Thinking about that on a graph, that means all of these would be okay, and so would 4. And the way to say that in interval notation would be from 4 to positive infinity. Okay? All right, now, if you had the graph of these guys, you could see from the graph what the domain would be, but it's usually a pain to graph, so people tend to want to be able to do it without graphing. But what would happen is y equals 3 over x plus 5 is a function that has two separate pieces that are part of it. And you'd have this gap right here at -5. So this portion would have all the reals from -infinity to -5. the x's of this would be all the reals from -5 to positive infinity. So that's why it turned out to be what it did. This one, if you were to graph it, would start at 4 and keep going to the right like that. And that's why the domain turns out to be from 4 to infinity. Okay? Now, there's some other functions that can have domain issues. We don't do them in Math 100, but in 112 we talk about logarithmic functions. And there you have to be positive you can't do the log of 0 or a negative number. And in trig, tangent, cosecant, secant are some functions that have domain issues. Okay? But there's just that handful, throughout all of your algebra that you have to worry about. And then I think it's interesting to note that functions that have domain issues, functions where the domain is not all real numbers, where you have exceptions, those are the functions that you have to check. You must check your answers when you solve an equation that's rational, or when you solve a radical equation. You have to check your answers. Okay? And later when you do logarithms, you could do all your algebra correct, but you have to check your answer to make sure that it works in the original problem. It's the ones with domain issues where you have to do that. All right, I need to do the function notation, but I'm going to stop the video at this point and just do that in a separate video.